So when ACI 237 Committee on SCC wanted to propose this session, it was really meant to bring some state-of-the-art knowledge of how to reduce the cementitious materials or the total binder of SCC. So as you know, SCC initially had a lot of binder, and we saw examples of why this is needed, because you need a high paste content. And binders could be, and I'm going go metric here, as high as 525 kilogram per cubic meter. And we see some binders now are all the way down to the lower 300s. So eco is eco-efficient, but also economical SCC. And one way of doing this, even the 530s had a lot of supplementary cementitious materials, and in some cases also limestone fillers or other type of fillers. We saw today an example of 70+% of slag, only 10% clinker. So when you see these very high numbers of cementitious materials, rest assured that very little of that is actual Portland cement. And I think this is obvious in this presentation. And Matthew will be presenting some work for Ecocem materials, where they have been working diligently for many years on the design of binders that are not the blended of different SCMs and Portland cement, but a binder that contains very low clinker factor. I have an issue with your presentation, although you're Canadian. It's self-consolidating, not self-compacting concrete, but that's European side of you. So without further ado, please help me welcome Matthew to talk about some of the technologies that have been introduced here in Europe and more recently in North America.
So thank you, Kamal, for an excellent introduction. So yeah, my name is Matthew Cruickshank. I'm a researcher with Ecocem Materials. I'm based in France, and today I'm going to be speaking about a rheological comparison of self-consolidating concrete prepared with high filler, low water Ternary Slag cement, and comparing that with an SCC prepared with a Portland-Limestone cement. And so my presentation today is going to be divided into three parts. First, I'm going to talk about why we want to use high filler, low water cements in a general sense. Next, I'll talk about the use of high filler, low water cements in practice, which is our Ecocem ACT technology. And then finally, I'll conclude with an example of the comparison I mentioned at the beginning in SCC. So first, let's start with why high filler, low water cements. So I think we all agree that in terms of where we are at the moment, we're in a sort of a climate crisis, and cement plays a big role in that. And so first, the cement and concrete industries, they currently emit too much CO2. No need to go into the details there. The demand for concrete in a global sense is so high that it's not feasible to replace concrete with existing alternatives, be it steel, be it timber, be it anything else that's available. We do and we will continue to rely on concrete for the foreseeable future. The best short-term solution for this problem is to use blended cements where the clinker is replaced as much as possible with SCMs. However, the commonly used SCMs, and the ones that we're most familiar with, such as GGBS and fly ash, are not available in sufficient quantities. And I mean that in a global scale. So the answer is blended cements prepared with SCMs that are sufficiently available geographically in terms of volume are the best solution. In terms of how do we measure this, so in about 2010, there was a research paper published by some Brazilian researchers where they developed a way to sort of quantify the sustainability degree of a certain concrete. And we have these two metrics, which are binder intensity and CO2 intensity. So binder intensity is quite simply just the amount of reactive binder per cubic meter of concrete divided by the compressive strength at 28 days. And so here we have to make a distinction between the materials that we add principally for their reactivity. So here we have Portland cement, GGBS, fly ash, and specifically not fillers. If we look at CO2 intensity by comparison, we're simply looking at the amount of CO2 released per cubic meter of concrete, so considering the aggregates, considering the admixtures, etc. And so if we look at CO2 intensity, that obviously favors a low clinker percentage. And so, for example, if we imagine a high slag mix, we'll be able to have a very low CO2 intensity. However, we have to recognize the fact that these SCMs aren't available and especially at the moment and in the future to provide a global solution to the problem. And so we also need to focus on binder intensity in order to keep the amount of clinker and also the amount of reactive SCM as low as possible. So as part of the same study, Daminelli, he did sort of a survey of both the academic and industrial data that was available. And what he basically said was that no concrete, or very few concretes, score below this line. If we look at the behavior up to 50 MPa, that's mostly due to standards and minimum cement contents. However, if we consider concrete higher than 50 MPa, that's typically limited by rheology, in that we can't reduce the cement content any lower because the rheology isn't suitable, and so we just don't do it. Since that research was published, a handful of research groups were able to demonstrate that actually we can produce concrete with a lower binder intensity than was previously identified. This was mostly academic, and it didn't really get out of the lab so much. I'll get to why in just a second. So what do we expect from concrete? Effectively, we expect from concrete strength, ease of use, so principally rheology, also cost competitiveness, and durability. And so if we look at the concretes that I just presented that scored quite low in terms of binder intensity, we had some questions surrounding ease of use. So we just talked about viscosity at the end of the previous presentation. If we're going to increase the water to make this work, we have big questions around ease of use, and specifically beyond slump, right? Really, viscosity is going to be the problem here. Slump, as long as you have the right selection of admixtures, 100% possible. So now I'll move on to the second part of the presentation, which is high flow low water cements in practice, which is our ACT technology. So a typical ACT formulation looks like this. We have about 50% limestone filler, 30% SCM, so the technology is compatible with a variety of both currently available and emerging SCMs, and then only 20% clinker. And so, as you can imagine, with cements like this, we need a reduction in the water to cement ratio compared to conventional concrete in order to ensure both strength and durability. And so typically, when we aim to reduce the water to cement ratio in concrete, what we do is we increase the amount of cement in order to compensate for that difference in paste volume. So if we imagine high performance concrete, for example, high performance concrete, we know that we have a higher amount of cement compared to conventional concrete. And so the sort of challenge that we're taking on here is to do exactly that, but without increasing the cement content. So for economic reasons, for environmental reasons, if for conventional concrete we say that we have to increase that cement content, that sort of defeats the purpose. So what we're trying to do is to decrease the water content in conventional concrete while not changing the cement content to have as small a disruption as possible, let's say. And so I can sort of resume how we do that right here. We have to consider the optimization of each of the components that go into our cement in terms of both chemically and physically. So we have issues such as particle packing play a big role in terms of, and also the size distribution. In order to have those strength and durability properties, we need to work at the lower water to cement ratio, as it has mentioned. And in order to make that work, we also have to be able to identify the correct admixtures that are compatible with this technology. And when we put this all together, we have a low carbon, scalable, and cost-effective cement. And we have concrete that is high performing in terms of strength, durability, and rheology. When we put that all together, that's what we call our ACT technology. So before I get to SCC, I want to give you a quick example in ready-mix concrete, just to show that this is a technology that isn't stuck in the lab, but it's currently in a demonstration phase where we have some real-world applications. So in late 2024, we built an entire building using ACT cement, not too far away from the Wembley Stadium in London. And so for here we had some ready-mix concrete that was poured, some elements were precast elements, and you can see the entire building here. And at the end of the project, one comment that came out was the project was actually kind of boring because the concrete compared quite similar to the conventional concrete that they were used to, and so they really didn't have a whole lot of comments. And that was sort of exactly what we were aiming for. So now I'll get to the third part, which is low carbon SCC, the high filler, low water cement versus a PLC. So this is an example of the sort of challenges we're facing at the moment in Europe. We have a potential client who sets the targets that are actually pretty straightforward here. They want a spread flow of 700 millimeters, and in terms of strength, they're looking for 50 MPa at 28 days. In terms of more qualitative requirements, they don't really want to mess with their mix design too much, and they want the rheological properties and the productivity of the plant to be more or less in line with what they currently have. So in Europe, sort of reference cement here was a CEM2AL, which is a cement with up to 20% limestone filler. And so I tried to take this example, and instead I brought in a PLC from the States, and I compared that with our ACT cement. I should be clear that the ACT cement I used here was what we call ACT 1, where the STM present in the cement is blast furnace slag, ground blast furnace slag. So to sort of demonstrate the extent of the issue in terms of strength development, here I've shown some mortar testing comparing the PLC with a water to cement ratio of 0.5 with our ACT cement at a water to cement ratio of 0.3. And we see that with this difference in the water to cement ratio, at an early age we have quite a low strength, but by 28 days we're able to achieve a strength that is higher than the PLC. So the mix design, they look like this. We didn't make any change to the cement content compared to the reference cement. Both mixes were prepared with 520 kilos per cubic meter, which translates to 875 pounds per cubic yard, I believe. The adjustment that you see here in the aggregates is just to compensate for the fact that with the ACT cement we're going to have a different amount of water, so we'll make sure it adds up to the correct volume. We use different admixtures in the two cases because of the different surface chemistry that we're going to have with our cement compared to the PLC. We have to consider that in order to achieve the desired rheological properties. And the difference in water to cement ratio that we end up with, so we go from a 0.5 in the reference mix and down to a 0.41 with the ACT concrete, demonstrates the extent of the rheological challenge that we're facing. I have a table here that summarizes the fresh state properties. So with the PLC, we end up with a spread of 670 millimeters compared to 710 for the ACT concrete, so both more or less what we were aiming for. In terms of the V-funnel, sort of a proxy measurement for viscosity in this case, the ACT concrete is slightly more viscous, but the difference is rather minor considering the difference in the water to cement ratio. In terms of the L-box testing, both concretes exhibit strong self-leveling properties, but not perfect. And we also measure a slightly higher air content with the PLC, which does favor a lower viscosity, which can explain to a certain extent the difference that we see. I also tested both of these concretes using a concrete rheometer to dive into that viscosity a little bit further, and it sort of confirms what I saw in the V-funnel testing, which is that with the ACT cement, the concrete is slightly more viscous as we increase the rotational speed, but again, the difference is minor considering the differences in the mix design. In terms of strength development, we see curves like this. So again, we do see that lower early strength development, but we achieve similar strengths at 28 days, both around 60 MPa, which more than satisfy the needs of the client in this case. So if I come back to the calculation of binder intensity that I presented previously, here with the PLC where it's about 90% clinker, so we end up with a binder intensity of 5.8 kilograms per cubic meter per MPa, whereas with ACT, considering we have that high limestone filler content, we're much lower at about 3.4 kilograms per meter cube per MPa. And so if I put this on the same chart that I showed at the beginning, we see that the reference concrete is in line with what we expect for concretes prepared today in industry, whereas the concrete prepared with ACT scores much lower. And that's basically it. So we believe that high filler low water cements are a good way forward. It's a scalable solution and that allows us to decrease quite drastically the carbon footprint and the sustainability of our concretes. The technology that we've developed, it's already on its way outside of the lab for practical applications, and one of those practical applications could be in self-consolidating concrete. Thank you.
Very interesting presentation. Thank you very much. Matthew, any questions, please?
One question: which was the fineness of the cementitious material? The blend.
So we play on the fineness and the particle size distribution of all three of the powder materials that we use. I'm not going to get into the details of exactly how it works, but it is key to play with the physical characteristics of the powders in order to allow that reduction in water content while maintaining reasonable viscosity.
Okay, thank you.
Thanks.
Very nice talk. I just had a quick question about temperature rise relating to some of the mass concrete work that I was talking about.
Yep.
Do you have any information on?
We have done some testing, so maybe if you speak with me after, I might
Yeah,
get
we
some
could talk
data.
offline.
I don't have the data top of my head.
Great.
Yeah.
I can answer that.
Do you want to just repeat that?
We've done some recent 1157 testing, and it passes a low heat of hydration type for 1157. So that'll give you the calories. So,
We can comment on the setting times.
the setting time, is fine. You just have to be real careful with admixtures. So that's.
Sure, that's my next question. Well, you go ahead with your question. I was going to.
Yeah, I just want to make additional comments. About 25 years ago, more than 25 years ago, in my PhD thesis, we have using a lot of limestone powder, and we also checking the heat of aeration. Absolutely, there should be no problem. It's much better because limestone powder is relatively inert, right? So the amount of the cement generated is that cement. So that's good. Can I have a question? Okay. Yeah, you use a lot of limestone powder. You have any data or something showing that about durability, such as carbonation or other properties? You have any? I don't mean that it is not good, but if you have a data, could be shared with the audience, would be great.
Yeah, so the two biggest questions at the start of this project were one, rheology, and the second, durability. The durability data that was available for concretes like this was quite promising, but there were still some gaps. And since then, we've been able to sort of fill those gaps with testing of our own, and the data has been overwhelmingly positive. We were actually quite surprised with how it performed in terms of carbonation, et cetera. I'm not a durability guy, but if you come see me after, I can share you some papers published by one of my colleagues that covers that in more details. Yeah.
But in general, you think that it's positive, right? It's no problem. Right?
So I can't hear.
It's positive, there's no problem. We don't see any issues.
Yeah, no, yeah. So far, no issues. Yeah.
Thank you.
Matthew, I was going to ask you to comment a little bit about the compatibility of the conventional admixtures in general with these low binder,
Yeah.
Low clinker binders in general.
Yeah. So there's a couple different things. So the composition of the binder doesn't contain any exotic materials. It's materials that we're already familiar with and that are compatible with PCs, et cetera, that are on the market. So you'll see in the example I showed here with STC, the admixture dosage was actually lower than for the reference concrete. One of the reasons for that is because we have a very low C3A content. So when we are working with concretes with a higher paste volume like this, we can actually see that reduction. The opposite case is when we're working in the example I showed with ready-mix concrete, where because we're not modifying that cement content, we are decreasing the water content, we're working at low paste volume. And that low paste volume concrete, the role of the admixture plays becomes more and more important. So I'll say that it's not not compatible with traditional admixtures, you just have to be much more careful about the selection and identification of those that are compatible.